So yeah, so exponential functions transformation. So as you know, the basic exponential function have these characteristics. So it has a base we call b, an exponent we call x, a coefficient for that base which we call a, and a constant which we call c. Is that clear?
Yes.
All right, so what's happening with an exponential function is that we're saying that the base has to always be greater than zero. Okay, all right,
Mm-hmm.
it has to be greater than zero. So b is the base, it has to be greater than zero, because if the base is zero and we have, let's say, the x, which is the exponent, is a negative. So let's say we have 0 to the negative 1. Okay, then what happens is that becomes 1 over 0. Yeah, okay,
Mm-hmm.
and 1 over 0 is what we call undefined. Okay, how many zeros are in 1? Come on, Sophie, you got this.
None.
Come on, there, come on.
Like the infinite.
Exactly, it's undefined. You can't tell. Okay, so how many zeros are in 1? We don't know. Right? We just don't know. Okay, all right. So that's why it does. That's why the base can't be 0, because if the exponent is a negative, then it will become undefined. All right. And just to define the exponential function, this probably started to come back to you. We did define the exponential function to be such function that which has all real numbers can be the exponent. All right. So the domain, which is x, is a set of real numbers.
Mm-hmm.
All right, it's an element of all the real numbers. That's what an
Mm-hmm.
exponential function is. So because it is defined for every single real number, which therefore includes negative and positive, then when the base is 0, when it's a negative, when once x, which is a domain, is a negative, then it will become an undefined function. Capish?
Mm-hmm.
We also say that the base cannot be, we said it cannot be less than 0, and it cannot be 0. Okay, so it has to be greater than 0. So what happens when the base is a negative? Let's say negative 3. Okay, well, if we have negative 3 to a power of a half, then that becomes the same as the square root of negative 3, correct?
Yes.
And at this level, can we find the square root of a negative number?
No.
No, we can't. Okay, we'd have to plug in an imaginary number which we call I, which we won't talk about. All right, so leave that there. So that's why we're saying, since it doesn't work, since a half won't work.
Question.
Yes,
What does I stand for?
Sophie, just go away. Go away. That's your homework. That's your. Well, I mentioned this to you a couple times. Do you remember?
Yeah.
Yeah, that's why. Yeah, good.
I'm still curious.
So if you're really curious, then when we're done, you go and Google. All right.
Mm-hmm.
So again, this is why because it can't be a half. When sorry, if the base is a negative, and let's say the exponent is a half, then that would be impossible. Okay, at this stage. All right. Cool. Same thing happens if the power is a fourth power. It will also give you any whole number of the denominator of the exponent will end up giving you an impossible situation. Okay.
Mm-hmm.
All right. Cool. Any questions?
No.
All right. So that's what we're saying, that the exponential function is that function which has its domain being all the real numbers. Okay. Cool. Now, in the exponential function, a has an effect. Okay. That effect, the effect that a has, is that a essentially can either be in one. So case number one, in our first case, if we have a function such that we have a being, let's say a is 2, and let's say that's 2 times b, let's call b 3, okay, to the x, and we're adding 0. Okay,
Mm-hmm.
now once you're adding 0, so I'm going to give you another case. If I keep this as put this as 3 times, I'll say 4 to the x, okay, and you're going to add 0, then what happens is that this will literally become your y-intercept. Okay?
Mm-hmm.
But it only happens when this is 0. So I'm going to put one more case because in math we always say it takes 3 to make a pattern. So let's call this 4 times, and I'll change the base not so that it's not too linear in our counting. Let's say 6 to the x, okay? Plus 0. All right? Okay, so I'm saying to you, Sophie, that once c is 0, okay, then in your exponential function, the a, which is now 2 right here, as you can see,
Mm-hmm. Is your
or
y-intercept?
is going to be your y-intercept. Because we know that at the y-intercept, x is always 0, correct? So if you plug 0 into this equation, into any of these, you end up with a 2. Isn't that true? You end up with the a value. So 3 to the 0 is 1. 2 times 1 is 1. Sorry, 2. 2. And it goes on and on and on. Is that
Mm-hmm.
clear? Is that clear?
Yes.
All right. But what happens when we change um, c from being 0? Well, when c changes from 0, you can tell me, so what's going to happen?
It's gonna change your y-intercept.
Right. So can you say a is going to be your y-intercept in this case?
No.
No. So this, you give me some arbitrary numbers to use, right, for these three
7.
examples. What? 7?
7.
Okay.
7.
Uh-huh.
7.
Sophie, go away. let's let's change the numbers.
7.
The 7, it sounds different, but it's the same number you said.
Sept.
Which one?
Sept. 7 in French.
Okay. That sounds like a new number. I'm like, what?
Also,
Okay, whatever. 8.
you also did
Whatever that one
7
is.
in Korean.
All right. So do we need to check them for you to see what I'm saying here?
Pardon?
Do we need to check it for you to
No.
see what's happening here? No. So the y-intercept will not be a in this
It'll
case.
be 9.
Well, great. And so the only thing you can do to find the y-intercept is actually plug in x to be 0 and then solve.
Mm-hmm.
And solve. Okay? Cool?
Cool.
All right. Now, actually, c has a function too. C is actually what we call the asymptote. And you know what asymptote is?
Yes.
Yeah. Which is? You said, what's
It's the line
yeah.
that it's constantly approaching.
Right. That's it. It's approaching but never gets to. So if we have 7, then this
It's
baby is
constantly
going to,
approaching 7.
y is 7, right? It's actually what we call the vertical asymptote, right? So it'll approach 7 but never get there. So it could be like this. It's going towards it but never reaches it. Yeah, it could be something like that.
That looks like it reaches it.
Like, go away. It could be something like that, okay?
That for sure reaches it. I think that passes it.
There you go. Ooh, don't do it. Oh, there you go. So it approaches it and it never gets it. That's what this value is. C. C is the vertical asymptote, that value that it approaches, but never quite gets to it. Okay? Any question?
No.
No. Moving on. So I like working with you and you're fast. Like a bullet coming from a sniper rifle.
I wish my class was fast.
I wish you. You'd be like, poop, poop.
And sometimes I end up like with the least work done at the end of the day because kids keep asking me questions.
Well, you're getting stronger because let them ask you. You're getting stronger and stronger and stronger.
But when answering the same question 20 times, it gets a little old.
Oh, yes, it does. All right, next problem, next step, Sophie. So we're going to look at transformation of the exponential function, okay? So like every other function, the general form is the same. So if I can rewrite this standard exponential function, f of x equal to that thing, okay? And I can literally rewrite it into this form.
That x looks like a y.
Which one? This x?
Yeah.
Well, there you go. Are you made?
It looks like a v.
Oh my! All right, so
That X also doesn't look like an X. It looks like two small brackets.
it looks like no, it looks like two asymptotes.
Yeah.
Okay, so S of asymptote is equal to, which is going to be represented X right now, is equal to, we're going to just
7.
expand this. No, we're not going to use the 7. We're just going to expand this into transformation form. There's going to be A, okay, times, well, A times B, well, I'm just, sorry, let's B, I'm going to expand this, B to the X plus D, okay? You put that in a beautiful bracket, and you put K outside right here, okay? And then you're going to be plus C, okay?
Mm-hmm.
So you know the effect that D has on the function, right?
I'm forgetting it at this current moment.
Oh, really? So D, we're saying plus D.
Oh, does D move it right or left?
Depends. If it's negative, it goes to the right. If it's positive,
Yeah.
it goes to the left. There you
Yeah.
go.
Yeah. I knew
Right.
that.
Oh, yeah, yeah. That's what you say. You don't remember it at
Yeah.
this moment. Okay. But there's one tricky thing about exponential function, Sophie. The base always changes. So we always need because we're transforming a function, and because we're transforming, it means that we must be changing something, right? And so what we always change in an exponential function is we're transforming the parent function. Okay, cool.
Yes.
So if we're transforming the parent function, then what this means is that in order for us to be able to describe a transformation, we must first be able to identify the parent function. Is that cool?
Yes.
Okay, so I'm going to give you an example here. If I have g of x, now that looks like an x, equal
Yeah, that bracket doesn't look very great.
g of x equal, and I'm going to use
7.
not use 7. Go away. All right, 7. I don't know what's wrong with you.
7.
Are you planning to go to heaven?
No, I'm just thinking it's Harry Potter's Quidditch number.
Oh my. No, no, you've watched too much of that now. Stop watching it.
I went through a phase in middle school. I know practically everything.
Oh my. And then you're watching it again.
Yes.
Oh
For
my.
probably the 50th time.
Ooh.
Yeah, I've read the whole series 3 times.
And watching the movie 50 times.
Yes.
Okay. Good luck, Sophie. Now I'm going to use S of x, Sophie of x. We try to get this one right. Good. There you go. Equal to, I'm going to use 3. Sophie, just go away with your 7. 3 to the x
Plus 7.
minus 2. Okay.
Oh.
Now, if I ask you to describe the transformation that maps this function g of x onto its parent function, again, we must always first identify its parent, okay? Now for this function, if you look at the two examples, the bases are different, correct?
Yes.
But well, every exponential function comes from the parent. And if I was to just write the skeleton of the parent is actually b to the x, okay? Every single exponential function is derived from that parent function. Is that clear? Hello?
Yes.
But remember, the base can always change, right?
Yes.
It's just that x remains the same.
Exponent.
X is always there, so it's exponent. It changed. The exponent is that quantity that can change, but in any exponential function, b can always be any value it wants to be, such as x. All right. So what's the parent function for this one? Give me your first try.
The parent function for
G of x.
7 to the x.
7 to the x. Good. So now
Yeah.
if I ask, yeah,
Okay.
that's it. Now you should take your wand and swish it and cast yourself a new spell. Okay, so we're saying that the parent function for this one is g to the x, okay?
Yes.
So we're transforming g of x,
Up 3 units.
well, in fact, we can't call this g of x because we said that is g of x. So we're going to call this h of x.
8?
H of x
Oh, h.
is equal to 7 to the x, okay? And that's the parent function. So you forget about all that noise, the plus 3. That's a transformation, okay?
Mm-hmm.
So now I'm going to ask you to describe the transformation that maps g of x, sorry, that maps, yeah, so that maps h of x, that maps g of x onto h of x. How did you get,
G of X
how
onto
did you,
H of X.
yeah, so how did you get g of x from h of x?
So how do you go from H of X to G of X?
Yeah, that's a transformation.
You move it up 3.
3 units what? Up
Up
3. So which axis is that?
Y.
Y-axis. Okay, that's it. Done. Next one, s of
That
x.
one, you move it down 2.
Oh my, what's the parent function?
3 to the X.
3 to the x. Okay, the first thing you should always do, you must identify the parent function. All
Yes, but
right,
when I look at it, I see the parent function.
I know,
So,
I know you're seeing it, but when you're doing the test, we don't know if you know it, so you have to just take. Okay. All right, Sophie.
yep.
All right, so that's just about that. Now, if I do something here, if I do that, no, what did I just do? I meant to put this.
C.
Let's call this 2 times, and we'll call this 4. Nope, not using 4. So I said all transformation follow the same principle, so I'm gonna put a half there. Okay, Sophie.
Okay.
All right, now describe the transformations now.
There's a stretch.
Is it what?
There's a stretch.
Which one? G?
Let's say we're looking at G of X.
Okay.
I can't remember if it's a vertical or horizontal.
Okay. Well, you're multiplying y by x
Mhm.
by 2. So if you're multiplying y by 2, what will that be? What kind of stretch will that be?
Vertical.
It'll be a vertical stretch. Okay. By a scale factor of how many?
2.
2. What a stretch? How does stretch go? Can you use your arms to show me how a stretch looks? What?
Right? Because like it would go from being like this tall to being like this tall.
Okay, yeah, you're stretching. You get
Yeah.
an elongation. Okay.
Yes.
All right, good. So you're a scale factor 2 stretch. What else?
It's been moved up 3.
And 3 units up. Which one happens first, really?
Yes.
Which one happens first? You just said yes. Which one happens first?
Yes.
How did yes happen first, Sophie?
The vertical stretch, I believe.
First?
No, I don't know.
Does it matter which one happens first?
Yes.
Mm-hmm. And the multiplication must take precedence over the addition.
So I was
Anyway,
right.
well, once you follow the concept, you must be right. But
Yeah.
you could actually do any one and you get the same answer anyway. But the multiplication takes precedence. Okay. So next one, can you describe this transformation here?
Vertical compression.
Okay. Scale factor of what?
2.
2. Okay. Now
So it'd
go
be
ahead.
like this to this.
Go ahead. Describe that transformation for me.
It's been vertically stretched by vertically compressed by a factor of 2, and it has been translated up 2. Oh, now it's also been moved left 3 and horizontally stretched, horizontally compressed by 2. Am I correct?
Which one are we talking about now? S.
I don't know, the one that you just wrote.
Oh, Sophie of X.
Sophie of X.
Okay. So go again for me, please.
So I've got a vertical compression of 2.
By scale factor of
2.
half.
Yes, half.
That's not 2. It's half.
Yes, half.
2 and half are 2 different numbers, Sophie.
Yes,
You know
I
better.
know.
You know better than this.
Yes.
Go ahead.
It's been moved up 2
Mm-hmm.
and left 3. And is that a horizontal compression?
Yep, because it's multiplied
Yes.
by by x.
By a half.
Okay, that's it. Horizontal compression is the same as a vertical stretch, correct?
Yes.
A vertical stretch is the same as a horizontal compression, right?
Yes.
All right, any questions here, Sophie?
Yes.
What's the question?
No.
Yes? You should say yes. You should say yes. That's what you should say. You should say yes. Question, yes. Any questions, Sophie? Yes. What's your question? Yes. All right, so that's pretty much what transformations are. Okay,
Yes.
any questions?
Yes.
Okay, what's the question?
Yes.
All right, so I'm waiting for the question.
I don't have a question.
Okay, all right, so let me see if I can get some questions for you to get done here for yourself. Whoa.
Moved up one. Second one's moved down one.
I want you to use the
Third
proper
one.
words. The first one is a vertical translation.
Trans-
Yes, thank you very much.
vertical translation up 1 unit.
Mm-hmm.
The second one is a vertical translation down 1 unit.
Mm-hmm.
The third one has been horizontally translated left 1 unit.
Mm-hmm.
And the fourth one has been horizontally translated right 1 unit.
Okay, good. Next one. This one. You may need to do some writing now, so good luck.
I need writing.
Maybe.
Do I really need to do a table of values?
Pretty much so. Go ahead.
Okay, my graphing calculator can tell me that.
What? No, manual.
It has a table of contents.
Oh my, Sophie.
I can tell you that one's been vertically translated up 1 unit.
No, that's not what I asked you to do. What table of values? Let's go.
Do you want me to like actually draw it out?
You know what? Forget about this question. You're bigger than this question. Um. Okay, go ahead. This one.
That one?
E E E
E.
E
Uh,
E.
uh.
It's not that's French, but
Yeah, it is French.
pencil.
That one has, the first one has been vertically stretched by a factor of 3.
Mm-hmm.
The, the next one has been vertically compressed by 1/2.
Mm-hmm.
And the third one has been reflected over my x-axis.
Mm-hmm.
Yeah?
Yeah.
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 No. Ooh, next one. Create a table like what? That nonsense. You're bigger than that.
No.
Describe a type of transformation you observe in part F. Predict what will happen to the functions that if you change that. Okay, go ahead.
The first one has been horizontally stretched by 2.
Scale factor of.
Scale factor of 2.
Mm-hmm.
The next one has been horizontally compressed
Mm-hmm.
by a scale factor of 1/2 or 1/2.
Mm-hmm.
And the next one has been reflected
Mm-hmm.
over my
Mm-hmm.
y-axis.
Mm-hmm. There you go. Next one.
Create a table.
Hold on. Okay, L. Do L.
Summarize my findings and describe the roles and parameters. So A is vertical stretches.
Okay, Sophie, next.
M,
Yep.
which change the shape of the curve. I believe it's like any of the stretches, because anything that's moving it right, left, up, or down, that's not changing the shape of it at all. It's just changing its position.
Mm-hmm. So those are just translations.
Yes,
Okay. Mm-hmm.
that's my answer.
A reflection change the shape?
Yeah.
How?
Wait, no, it wouldn't change the shape. It's just
Just change the
changing the
direction.
orientation. Yeah.
Mm. So it's just either compression
Stretch.
or stretch. Okay. Next one. And
Which transformations change the ones that change it? The
yeah, which
ones
one?
that, yes, the
The location of the asymptote.
transitions. Yes.
So which one changed the location of the asymptote?
The constant at
Yeah.
the end.
Okay. Which one? Which transformation? Reflection
The
enlargement, reflection enlargement, rot rotation,
reflection
translation.
here,
Which
rotation
one?
here.
Which one changed the asymptote? Come on, read it for yourself. You got this.
The one that moves it up and down.
Okay, so that's which one? Which of those letters? C?
C.
Yeah, that's C.
I
Oh, no,
said that like
I didn't hear.
45 seconds ago.
Really?
Yes.
I definitely wasn't listening. Next.
Do they affect in the same way? Um, I don't know.
Well, find out. Go ahead.
Do you want me to like transform them?
Hmm? Trans-
Um, I'm gonna say yes.
yep. What's the reason?
Well, if you add a constant to the end of anything, it's gonna go up. Tack a multiplier thingy in front of anything, and it's gonna vertically stretch it. Um, yeah.
Okay, so do the transformations affect f of x equal b of x in the same way they affect f of x equal x? F
I
of
have
x
a
equal x
feeling
squared.
not completely.
F of x equal x squared. Hold on,
I'm gonna say yes.
I don't understand the question myself. So
Yes.
do the
I don't like this
transformations?
question.
Huh?
I don't like this question.
It's not you don't. It's not everything that you like you get.
I know, but I just thought it should be known.
Oh my. Do the transformations affect f of x? Do the transformation affects b of x in the same way it affects x? Which transformation? F of x equal x squared? What? Do
I
the
think it's
do,
asking if you were to transform each of those functions using the same method, would it do the same thing? So, like, if you were to multiply it by 2, is it going to do the same thing to both of them?
nope. They're asking you if those transformations, Sophie, come on now. Instead, take my time to read the question. They're asking you if the transformations you describe above affect
It doesn't say
these.
above.
It didn't have to, because what you're saying wouldn't make any sense now. Multiplying what? By x squared? No way. So they are making reference to the transformations that we described above.
Yeah.
So will they affect it the same way? This
Yes.
and this the same way?
Yes.
Really?
Yes.
Sophie, f of x equal x squared.
Mm-hmm.
Transforming the shape of the curve. Okay, so all of
Well, the curve's shapes are
the-
different to begin with.
these are all curves, right? Yeah.
Yes.
The asymptotic function 1 over x is well, it's not a curve, but well, if it's not a line, it's a curve. It's just not a smooth curve, so it's a curve. Um, the square root of x plus or minus does form a curve too. And the absolute value of x does give you a v-shaped curve. So all of those four here are curves. So do the transformations affect this b to the x in the same way they affect f of x equal x?
I'm
F of
gonna
x equal x squared.
I'm gonna take a guess here and say no.
All right, which transformation did we say change the shape of the curve again?
Stretches.
Yep, does it affect this the same way? Yeah,
Yeah.
a will change their make them stretch, right?
Mm-hmm.
Hmm. Even the f of x equal x, that's the linear function, right? It will stretch. Yeah. What about the location of the asymptote?
Yeah.
Yeah. So it's this pretty much is a summary. So is a summary because we realize that the effects are the same. It doesn't matter which of the functions you're looking at. The effects just remain the same. Cool.
Cool.
All right then. Next question, Sophie. Ooh. We did a lot of these already, about a month or two ago.
Okay, I probably forget most of it.
Okay, go ahead. Try this problem.
The yes.
Mm-hmm. Check
Describe
it.
each transformation.
Yeah, yeah.
First one has been
Can you move to the second one, number two, please?
number 2. Oh, okay. It's been vertically stretched by 3 and reflected over
Can you
the
pause? Pause, please. Can you
axis.
can you do D for me? Sorry, Sophie, but do D for me.
D,
Number one D.
number 1D.
Sure.
Oh, okay. It's been vertically stretched by a factor of 3 and horizontally compressed.
Hold on. Did you say vertically
Okay.
stretched by a factor of three? D, number one D?
Yes.
How?
Vertically stretched by. Oh, wait, is that 3 a base?
Uh-huh.
Oh! It's
Oh!
been horizontally compressed by 1 over 3.
By one third?
Yes.
Okay. Are you sure?
No, but yes.
Make up your mind. You're sure or you're not sure? Which
Yes.
one? Let me use my language. Me say be sure or you're not sure. Which one?
Pardon?
You're sure or you're not sure?
I'm sure.
Yeah, you get what me I say?
Pardon?
Yeah, see what this has to you?
What?
Me say, yeah, see what this has to you?
Huh?
That's exactly what French sounds like to me.
Same.
Look at the problem, Sophie. It's x over 3.
It's 3 to the power x over 3.
Yep.
Can I interpret that
You
in
get
the
right.
same way as 3 to the power of 1 over 3 times x?
Yep.
So it's a horizontal compression of 1 over 3.
That is correct.
So I was right.
I believe so.
Cool.
Uh-huh. Next. Can you go back down to now number 2?
Number 2a,
Yep.
vertical stretch of 3 reflected over the x-axis. Yes.
Mm-hmm.
And it's been
Yep.
moved left 1.
Mm-hmm. Next.
B or C, because they've laid it out weirdly.
Everyone.
C. Vertical stretch of 7, and
Mm-hmm.
it's been moved right 4 and down 1.
Mm-hmm.
Mm-hmm.
Okay.
Now B.
Will it be an exponential growth or a decay?
Decay.
Why?
Because the base is less than 1.
Okay.
Yes?
Yep. That's it.
Okay. Now B, it's going to be a vertical.
Not that is less than 1 because it's a fraction.
It is less than 1 if it's a fraction.
Are all fractions less than 1?
No, if
So,
it's
so
an
that's why I'm
improper.
trying to back you up there. But by the way, if it's a fraction, if it's 1.5, will it grow or will it decay?
Grow.
Okay. Okay. Carry on.
Um, B, so vertical stretch of 2, horizontal stretch of 2, and up 3.
Mm-hmm.
And the next one, it's been moved right 6, and there's a horizontal stretch of 3.
Okay. Next one. Number 3.
I can't even see the functions.
State the
So
y-intercept, the equation of the asymptote, and the domain and range of each function in question 1 and 2. Oh, sorry, my bad.
So x is going to be like any number, any
What?
real number.
You
For
said
a
A?
of 1, x
For
is going to be any number.
for A, what?
For a of 1, my domain is
For number 1A, you said?
yes.
You said A of 1. What are you talking about?
A of 1, 1a.
Sophie. Sophie. I hear A of 1, I'm like, what? What is Sophie talking about? Is it an answer you're giving me or what?
For 1a,
A of 1.
my,
Uh-huh.
my domain is going to be any number.
We can start at the y-intercept. What's the y-intercept?
Y-intercept is going to be 0, 3.
0, 3. Mm-hmm.
Yeah. And my range is going to be anything greater than 3.
Mm-hmm. And
My
your range is gonna,
asymptote,
and your what? So y-intercept, the equation of the asymptote. What's the equation of the asymptote?
y equals 3.
Mm-hmm. The domain and range?
I already did that.
Oh, I didn't hear.
My domain is any number and my range is anything above 3.
And your range is anything above 3
3.
because it approaches 3 and never gets. Is it above or below 3?
Below 3.
You sure? Because
No.
you were very confident just now.
I know I was, and now it's above 3, right?
Sure?
No, it's below 3.
Mm-hmm.
It's
No.
below 3.
Uh-huh. No, we're stuck. How do we
It's
know it's below
below
3?
3.
What's the y-intercept?
0, 3.
Okay, so it's 0, 3. So you know it's gonna be. Is it below or is it above? Make up your mind now.
I don't know.
Come on, Sophie. Do a sketch. Do a sketch in your book. Go ahead. So 3 is both the y-intercept and the asymptote.
That doesn't work then.
Mm-hmm. How so?
Because it can't be constantly approaching a number if it's on the number.
Mm-hmm.
Hmm.
So it's 3 to the 0, which is 1, which is 1, and 1 plus 3 is 4. The y-intercept is 4, Sophie.
Ah.
Oh.
Ah.
Uh-huh. The y-intercept is 4. So it is clear the graph is going this way
How is that clear?
because for the y-intercept, if the asymptote is 3 and the y-intercept is 4, it has to be going this direction
Why
instead of
can't it go the other way?
where, this way? Or is it going to pass 3?
No, like this way.
Which way? This way?
Like a growth. Like
Okay, it could be. It is well, it is a growth. So my bad. For examples, for the sake of proper example, that would be the better example.
so I'm right.
This would be the better example. Something like that.
Yes, that's yes.
Yeah, but it couldn't be anything down here, right? So we know it's a growth, but it couldn't be down here. Because if it's down here, it has to pass 3 and to get to 4.
Mm-hmm.
Okay. All right, next one.
B. My I can't say that word. The
Asymptote.
asymptote.
Acetote. Acid tote, Sophie. Acid tote.
It's your tote of acid.
Asymptote. Asymptote.
Asymptote.
Yeah, that's it. Don't bite your
That
tongue now.
thing. So that thing is going to be y equals 0.
Which one? Which one are we doing now? A, B, or C?
B.
Okay.
B of 1.
So the y-intercept. Let's start at the y-intercept.
My y-intercept.
Yep.
It's gonna be, goodness, I'm blanking. It's gonna be 27.
327. What?
right?
What?
Because if I plug in 0 for,
3 squared is what? 27. Yeah, carry on.
that's not squared, that's cubed.
Yeah, I mean cube. That's what I meant.
Yes. My domain is going to be any real number, and my
Yep,
range
always
is
so.
going to be anything above 0.
Keep going.
Yeah. I think I covered everything.
See?
See?
What's the asymptote? Asymptote.
That was the first thing I said.
Which is what? 0?
Yeah.
Oh, okay. Carry on.
Um, the asymptote for C of 1 is going to be y equals 0.
Mm-hmm.
My range is going to be anything above 0. My domain is going to be any real number. And my y-intercept is going to be 1/3.
Okay. Can you move to question number 2B, please?
Two of
Two.
B of
Can
2.
we do 2B, please?
B of 2.
That works. BF2.
Um, my asymptote is going to be y equals 3.
Mm-hmm.
My domain is going to be any real number, and my range is going to be anything above 3.
Your domain, you said it's gonna be what? Any real
Domain is
number?
going to be any real number.
Are you sure? Just asking.
Yes.
Okay.
And my range is going to be anything above 3.
Mm-hmm. Your range is gonna be what? Anything above 3?
Yes. No,
Why
below
above?
3.
Why?
Above. Yeah, it's above.
Why above and not below?
Because it's a growth.
No. Number B.
It's a decay. It's going to be below 3.
Ooh, what? This is funny. How you sure this is a decay?
Yes.
How sure are you that's a decay?
76.57%.
Okay. Do you know that sometimes when the base is half, a fraction, it's not necessarily a decay?
Care to elaborate?
Oh, I think I can. So let's let me try to find an example. Hold on. Why did I bring this up now? Yeah, keep doing those so until I get the problem to show.
Okay. For A of 2, uh, the y-intercept is -12. The asymptote is going to be 0.
Oh, happy day.
The domain is going to be any real number. And the range is going to be anything below 0. Sure. For C of 2, the asymptote is going to be y equals -1. The domain is any number. The range is anything below -1. The y-intercept is
Okay, here goes one, Sophie. You can stop.
okay.
You can stop. Here's the question. So we have here's a problem. Y equal 1.5. I meant 1.5.
1.5.
Yeah, 1.5. That's a point, okay? 2 to the power of x plus 4. Okay. Would you say that's a growth or a decay?
I'm gonna say it's a growth.
Mm-hmm.
Wait, but you said that one, like, the fraction would be the base. In this case, the fraction isn't the base.
Yep. So that's a whole number, right? So that should be a growth, right?
Yeah.
Okay. Try to plot that graph. Try to find the points, and you'll see what's happening. Just try to plug in about use x is -1, -2 to +2. Use those two domain values, and you'll see what happens.
I'm just using my graphing calculator.
Yeah, that works.
It's a growth.
Is it a growth?
Yeah.
Are you sure?
Yeah.
You're certain?
Yeah.
You certain, Sophie?
Yes, my graphing calculator is certain.
Mm, Can I see what your graphing calculator gives you? Yeah. So we're saying when you do this one, do you get a decay, correct?
Mm-hmm.
And we're saying even though the base is a positive, you can't just randomly say that because the base is a positive, then you're gonna get a growth. Okay?
Mm-hmm.
You have to factor other things into the whole problem. So not because the base is a positive does not mean that you will get a growth.
Well, 0.5 is a positive.
I mean a whole number. A whole number. A positive whole number. Well, all whole numbers are positive. Okay? Or a counting number, so to speak.
You can count in quarters.
Sophie, counting numbers. No one counts. No one counts quarter,
I'll count in decimals.
2/4, 3/4. No, we have the counting numbers or the natural numbers are 1, 2, 3, 4,
0.25,
5. Nope, nope,
0.5,
nope. Those are not natural.
0.75.
Those are decimals. Those are decimals. All right. Do you get the point that I'm making here, Sophie?
Mm-hmm.
Right. So not you can't just look at it and say, oh, it's a whole number, so therefore it is. Therefore it is. Yep. You can't. You have to look at other factors. All right. Next, let's continue.
With?
You finish all of those there. We're done with those.
Yeah,
Let's
I'm
go
done with
into
those questions.
practicing. We're just gonna do C here. 4C.
4C.
Yeah, 4C.
Well, of course, you go for the hardest one. Vertical stretch of 4, been reflected over the x-axis. 6 down, 9 left, horizontal stretch of 3.
You done?
Yeah.
Okay. Okay, so here goes something for you to do. Question 7.
Why do they have to make it T of T?
I know.
I have to sketch the function?
The question is right there, Sophie, right there. What you don't like.
I hope you know how awful this drawing is going to be.
Yep.
It's not really to scale.
Okay.
Well, that sounds boring.
By the way, can you show me a graph one more time, Sophie?
Yeah.
Mm-hmm. Okay. It looks the direction is quite fine. Everything else is all right. Wait, just to note, Sophie, when you're doing the graph like
Yeah.
these, always draw your transformation, the parent graph first, and then transform it, right?
Okay.
That's all the that's the strategy. You might find a way around it, but for consistent in lesson, draw the parent function first, and then apply the transformation. Cool.
Mm-hmm.
All right, next one.
Question.
Yep.
What is that equation? Oh, n to the zero is the initial population. What's the initial population? Shouldn't it tell me that? Or can I assume that it's zero?
Where n of 0 is the initial population. So initial population is 0. A is
Yeah.
0. Therefore, A
Then
is 0.
would I just take that two to the t over whatever that is and multiply it by zero? So
Hold
then isn't it
on.
zero after any amount of time?
Hold on. Let me see the question myself. The doubling time for a certain type of C cell is 3 hours. The number of cells after T hours is described by N of T equal NO equal N of T equal NO 2 to the T thirds. T thirds, not 2/3, but T thirds. Where NO is initial population. How would the graph of this equation change if a doubling time were 9 hours? Okay. The
How
first
would
question,
it change if the doubling time was multiplied by 3?
yeah, it means that the base would be 3.
Mm-hmm.
Yeah, because the doubling, the scale factor, that's R. Remember when we looked at exponential function at one point, and we looked at uh oh, what's the name again, Sophie? It's gone off my head. Uh Arithmetic sequences and geometric sequences. Remember that one?
No,
Really?
I probably do, but I don't remember it based off of the name.
Okay, all right, fine, no problem. But what we're saying is that R, the doubling, any amount you're increasing by the scale factor, that will be what your base of is. Okay.
Mm-hmm.
So if you're increasing by a factor of 3, your base is gonna be 3. So how would the graph of the equation change if a doubling time were 9? If a doubling time were 9 hours? Well,
Well, just
yeah.
take that equation and multiply it by 3, so a vertical stretch of 3.
What?
Would it be a vertical stretch of 3?
No, the base changes. The whole
Oh,
the whole function
would
changes.
it be 6 to the
Can't be 6. It's gonna be 3 to the something like T thirds. You
has to
know,
be 3?
yeah, because if
Then
you're
why is 2 for the one that's 3 hours?
well, that means that what that means is that you're increasing by a factor of 2. Yep.
Okay.
It says doubling. So
The
how would
doubling time for the original one is 3 hours.
yeah, it's 3 hours, but then the factor here is 2, so it's 2 times that. But this times it is 3 times that for the second. So every time it increases, which is every time it doubles, it's going to be doubling, not increasing by. It's not going by a factor of 2 this time. It's doubling by a factor of 3. Yeah,
Yeah, so the time axis is going to be the same, and then the growth axis is going to be tripled.
pretty much. It's going to shift. So pretty much what's going to happen here
It's just a
is
giant stretch.
yeah, yeah. It's going to be a stretch.
Yes.
It's going to be a stretch. But the base changes to 3. You get that
Okay.
concept?
Yes.
Yeah. So if it's double, hold on. How would the graph of well, let me read this question one more time. How would the graph of the equation change if the doubling time were 9 hours? If you're doubling, the doubling time for a yeast cell is 3 hours. So which means every 3 hours it doubles, right?
Mm-hmm.
So every 3 hours it doubles. How would the graph of the equation change if the doubling time were 9 hours? Hold on, Sophie. Think about this
So
one more time.
initially, it would look like this. And now it's looking like this.
How?
It's a lot steeper. It goes up quite a bit faster. Wait, no, doubling time we're 9 hours, so it's going to be a longer.
Slower. Yeah, it's a
Slower.
longer. Yeah, it's gonna be
Yeah.
a longer. So it's gonna be a compression. It's more like
Yeah.
it's a vertical compression, right?
Mm-hmm.
It's elongating. It's not stretching. It's elongating. Follow. It's not well. Elongation and stretch. What I mean is this. That's your axis. So
That's my Cartesian plane.
yeah, that's your Cartesian plane. It should go under normal circumstances. It would be like this, for example.
Mm-hmm.
If the doubling time is not every 9 hours, it's gonna go a little bit wider.
Mm-hmm.
Yeah. So it'll be less steep. Okay. Yeah, that's the question. How would the graph change? It becomes less steep. So that's the answer.
Yeah.
Yeah. Next one.
What are the domain and range of the function in the context of this problem?
Yeah. What's the domain?
The domain is anything above 0.
Mm-hmm. Why not less than 0?
Well, you can't have
0 time.
yeah.
I mean negative. You can't have negative time.
Yes.
Yeah. So in that context,
And
don't really. Mhm.
the range, we know the range is anything above 0, and the domain is anything.
No, the domain can't be negative. You can't have negative time.
Yeah. Wait, is time my x or my y-axis?
X.
X.
Time is always independent, which is any independent variable is always on your x-axis.
But then right there on your x-axis, you have negative numbers.
Where? Over here?
Yeah, like it goes past.
Come on, I was just drawing at the thing. All right, let me change it because I can't manage you so many times here. Sometimes I can't manage you. Let me change it. To be honest and realistic, you can't have negative time. So it would look like this, for example, and then if the doubling time changes, it looks like that. Okay.
So basically, both of them are just anything above 0.
Which one?
Both your domain and your range.
R above 0? Yeah, pretty
Yeah.
much. Pretty much.
Yes.
Yep. So this is one of the cases where your domain and range can't be less than, it can be negative.
Mm-hmm.
Okay. Next one. By the way, let's do this question, and I'm gonna need to touch base with something else.
Mm-hmm. Well, of course, all the constants are 3.
What's the question? Match equation of the function from
The
the list.
appropriate graph on the next page.
Oh.
Oh. Yes.
So how is this gonna work now, Sophie?
Um.
All right. So there goes 2. Can you see those 2?
Yes.
Okay. So and then see if those 2 match these 2.
Okay, maybe you scroll up and I'll take a picture of the equations
Okay.
on my phone.
All right. Do that.
Okay.
Got it?
Yes.
So how am I gonna know when you're right or wrong? So I need
You're
to take a pic.
not.
I'm gonna take a pic too. Oh my. All right. So let's see.
Okay. So A has been reflected over my x-axis and my y-axis. Huh. Same thing with C. B doesn't have any reflections. It's a decay. B is a decay. So therefore B has to be 2.
So B is a decay. And you say B is what? 2?
2?
But 3 is a decay too.
Yes, but I'm taking a guess.
Oh. Don't guess. Use the
Wait,
first.
no, because that also
Apply it.
matches my y-intercept. My y-intercept is 4, so B is 2.
Your intercept is what? 4?
Yes.
Yeah, B is 2. Correct. That looks perfectly correct.
Okay.
So we are one down.
Yes.
One score.
um. Okay. Hmm.
Let's find A. Let's find A.
Let's find it. Okay. Maybe if I'll find my y-intercept and yeah.
Yeah, use your strategy. Apply yourself. That's why you got the question. Match it. You have to apply yourself.
2.
Hmm?
2.
What? 2 is what? A?
Yes, that's my
Can't,
y. No, that's
can't
my
be.
y-intercept. My y-intercept is 2.
Oh,
Yes. And
let me check that
oh,
myself.
okay. And I flipped over my x-axis, which gives me present.
Can't be. Yeah, 2.
Mhm.
So which one has 2? Oh, so the answer is between 3 and 4 for A.
Yeah.
Yeah.
I'm gonna say it's 3. No.
Asymptotes. Mm-hmm. Now you need to just determine if it's a decay or a growth.
Yes, which is a problem because it's flipped over both my y and my x-axis.
Okay. So
So A, basically I have a decay. Then I flip that over, which gives me a growth. And I flip that over again, which gives me a decay.
so draw the parent function first.
I did.
Okay. Or just plug the values in. That works. Like just throw whatever.
I'm
Like
gonna plug
a domain value into the equation and see which one matches. Like there's no strategy that is set in stone here. But
I'm
there's
gonna plug 1 in.
one really? One really?
2?
Let me see. Yeah, one will work because none of
Yeah.
them have the same value of x of y for one. So go ahead. That's gonna be 1/4. There's negative 1/4 plus 3. That's gonna be what? No, that's gonna be 1 over 1/4. What the? So it's gonna be 4, negative 4. Negative 4 plus 3. That's negative 1. So it's 1 to negative 1. Where is that one? That's the answer. Number 3.
It's number 3?
Yeah,
Yes.
one corresponds to negative 1. Did you get the same answer?
So, yes.
Because
So A is number 3.
yeah.
Yes. So now we've got C and D left.
Mm-hmm. Should be too difficult.
Wait, isn't D a growth and then
That C and D. Good luck, Sophie. Good luck. Well, there's a negative exponent, which indicates that
wait. Let's just find
C,
the y-intercepts of each of them.
that won't that. Hold on. C and D.
Works. Yes.
Oh yeah, because they have different y-intercepts.
Yeah.
But I'm gonna tell you, by the way, C is actually a growth, and the D is a nope. Yep. Nope. C is a decay, and also is D. Hold on. Hold on. That will be a reflection. So the negative exponent and the fraction. Oh, that's not a fraction. That's a whole number. It's gonna grow.
D is 1.
What?
D is 1.
D?
Yes. Is 1.
The y-intercept you're saying is 1?
No, the graph it fits with is 1. The y-intercept is 5.
For what? For D?
The equation D matches
Oh,
graph
so there's
1.
not one, graph I.
I.
Because I'm like, where's one? Which one? Which one? I. Mm-hmm.
Therefore, through the process of elimination, C is 4. C is 4, not wait, it is not it's in Roman numerals. So it
Uh,
is 1 and it is 2 and it is 3.
Sophie, if you say one, I don't. Let me
I'm
talk.
not gonna say, oh, graph C matches with or equation C matches with graph IV.
Oh yeah, that's what I like what? Four? Oh come on. Anyway, so all right. So before let's just address something here, Sophie, before we order time. Okay.
Mm-hmm.
So let's say we have the exponential function. Okay.
Mm-hmm.
Um, 3 to the x. Okay.
Mm-hmm.
And we have 3 to the x equal to 9. Okay.
Mm-hmm.
And some would ask you, what is x? What is
2.
x? Yeah, whatever. X is 2. But how do we find x is 2 when we have more complicated situations? For example, when we have this 2 times 3 to the x equal to, sorry, plus 1 equal 25. How do you find your answer?
Can I attempt?
Yeah, go ahead.
It's not a friendly number.
Okay. So what's the number?
So what I'm at right now is 3 to the x equals 12.
You got 3 to the x equal 12. How did you get that?
I subtracted 1 and then
Yep.
divided by 2.
Okay. That's good. So we have, so just going through this, you did the same solving equation. So you're left with 3 to the x, right?
Mm-hmm.
Equal to
12.
12. So it's 25. 25 minus 1 divided by 2, which is 12. Okay. And then what?
I'm thinking.
Mm-hmm.
Mm-hmm.
1 minute and I'll jump in. Sophie, are you still there?
Yeah. Okay, I'm taking a guess and saying it's around 2.27.
Wow. Okay. So let's go through this. Ready to go through it together? So that's your answer?
Yeah.
Okay, so let's go through it together, Sophie. So you see from this basic example, 3 to the x equal 9, you know the
Mm-hmm.
answer is 2, right?
Yes.
Well, one of the strategies here would be first strategy if we're looking at logs, which we're looking at the opposite of an exponent, okay? All right?
Mm-hmm.
So that's what we're looking at. So we have 3 to the x equal 9. Well, there are two ways to solve this problem. Well, we could equate the bases, and therefore we'd get 3 to the x is the same as 3 to the 9. 3 to the 3 squared, correct? Because that's the same as 9, right? And then when we just drop the bases and we say that's x equal to 2. Cool?
Mm-hmm.
That's easy. But then there's another situation. What we can do is we can find the opposite of the exponent, which is log. Okay? So let me erase that. Which means what we could have done is this. We have 3 to some number give us 9, right? So
Mm-hmm.
we could literally drop the base, drop the exponent, and this is rewritten as x, bring the x down and write x log. Our base becomes 3, okay? And we have something in an exponent power here called 9, okay? Follow me?
Yeah.
Okay, so we have x log 3. So let me just erase this 9 for now, by the way. X log 3, and that's equal to what number again?
9.
9. All right? Is that clear? So now what we do with this is that we're just going to go one last step. So we're going to say, what's x? Well, x equal, we're going to bring this log over there. All right? X equal to log baby 3 here, base 3, 9. Okay?
Mm-hmm.
So I'm going to just get a log calculator. I did ask you the last time we met to find out how to use it on your calculator, right?
I still haven't.
Really?
I need to write that down.
Yeah, I'm going to show you 1 second. Hold on. So I need to go on internet. Let me get the right page. All right. Let me know when you're seeing the screen, Sophie.
No.
Okay. So what we had on the board was, let me just rewrite it. So we had 3 to the x equal 9, right?
Mm-hmm.
And we're saying that it's the same as saying log. So we drop the x and it becomes log. The 3 becomes the base. 3 to the 9,
9.
all right? That's what's going to be equal to x, okay? Is that clear?
Mm-hmm.
So what we're saying is, what number do you raise 3 to get 9? And that's what's going to be equal to
Yeah.
the x over there, okay? Got that? Sophie? Sophie?
You cut off.
Oh yeah, am I back now? You're hearing me?
Yeah.
Okay, so we say log base. You see where we see the base here? Log
Log base
3,
3 and then 9 on the top.
and then 9 on
And
the
then it'll
top,
tell you a number.
and then it'll give you a number. The number is 2. Okay?
Okay.
Got it?
Yeah, I knew that, but yeah.
I mean, yeah, but I'm just trying to show you the principle, okay?
Mm-hmm.
Okay, so it's the same principle with the last problem we had, right? So
Yes.
we worked it out and we got, what did we get again?
So just take that 9 out and put it in the 12.
So it was base 3?
Yeah, it was.
Yeah, okay. So log base 3 to the 12. 2.266 blah 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 blah.
Do we remember what my guess was?
Yeah, 2 point something something something.
2.27.
Oh, yeah, yeah. That wasn't the guess. That was you calculating. Go away.
I was pretty close.
You're just as perfect as it comes. Okay.
Okay.
Any questions there?
Nope.
All right. So let me just give one more that looks a bit more complex while I'm on the log calculator here. So this one would be, let's say we have, I'll keep the base as 3. 3 to the x plus 1. Okay. And that's equal to, I'll make it 9. Okay. So what's x? You want to try that for me?
X is 1.
Really?
Yeah.
Oh, hold on. Let's, oh, yeah. Go away, Sophie. Go away. 15. That's that one you won't be able to guess. But you know what, Sophie? Before you do that, I want you to show you the principle.
Log base 3,
Let's
put the
keep it at
15
9.
in where the 12 is, and then
Hold
whatever you
on,
get out,
hold
subtract
on,
1
hold
from.
on. And then I'm going to change the question to 3 to the x plus 1 equal 15. Okay, let's do this one standard way. So we know the answer is 1. Yeah?
Yes.
So let's see if we can go the standard way. So the standard way is we drop the exponent, correct? Hello?
Yes.
So this become x plus 1. Yeah?
Equals 2.
No. X plus 1. I could just put x plus 1 equal to log, log. The base is 3. Yeah?
9.
9. Where are we done?
Are we done? No.
Huh?
Yeah.
No? Okay.
No, you're
So
not,
let's
because you don't know what X is.
okay, let's keep going. Let's keep going. So do we know what log base 3 to the 9 is?
I do, but you can plug it in.
Yeah, what is it going to be? 2.
2. Then
Okay.
subtract
And
1
then
from
subtract the 1. And there you get 1. Okay?
Yeah.
So now you apply the same principle here.
So log base 3 to the 15, and then subtract 1 from that answer.
Okay. So log base 3 to the 15. What is that? Something?
Something.
15, whatever that is. Oh Lord. Can you subtract 1 from that thing?
I mean, yeah.
I mean, go.
1.4649735207179.
Okay. So so can you try it? You're gonna go. So it's gonna be x, which is 1.2.4. That number plus 1, which is gonna be 3 point that number. So it's gonna be 3 to that number. That's gonna equal 15. Okay. I'm gonna try it. Just roll it off. Put it 3 to the power of 2.474. 2.4.
No, it's going to be 3 to the power of 3.46 because it's plus 1.
Yeah, 3.465.
I'm typing in all the numbers.
Oh my.
That gave me 45.
Say again?
It gave me 45.
What? Let's see what has happened here. So
I think that's because you changed it, though.
what?
Didn't you change it from being a -1 to a +1?
It's plus 1, so it's minus 1. Oh, it's supposed to be 1.46. Hold on, Sophie. Hold on.
3 to the power of 1.46
Hold on, Sophie. Hold on. Yeah, so it's supposed to be 1.46.
gives you 4.92 or 4.972.
But then when you add the 1 to it, it's supposed to be the final thing supposed to be 3 to the 2.465.
Yeah.
Yeah.
Yeah, that's right.
Yeah. All right, so that's pretty much that, Sophie. So that's that. Those are the rules of logs that you need to know under this principle. Okay.
Okay.
Most times I don't know if you already encountered with the addition or
Yeah.
subtraction in the exponent.
Yeah.
All right, but that's pretty much how that's done. All right.
Yeah.
Until then, we'll meet next time. See you next week, Wednesday. All being well.
Okay.